Thank you. So, as you said, my name is Sylvain, and I'm going to talk to you about GSM and more exactly how to hack cheap cell phones and make them act as the network. So I'll first start with a short introduction about GSM so that hopefully you can follow the terms and technical stuff that I talk about in the rest of the talk. I will introduce the Calypso architecture, which is present in this phone, and then finally I will dig into how you can hack this phone, even more than it already is. So, what do I want to do? I want this phone, which costs like 20 bucks or something, and have it broadcast its own network so I can, take another phone, scan the network, and register to it, send SMS, hopefully send call, and this kind of thing. Why would I want to do that? Well, several people have proposed use case for it, and honestly, for me, I just wanted to see if it was possible or not. That's pretty much the only reason I did it. So why this phone? Well, I hope that at least some of you are familiar with Osmacom BB and know that this phone is really flexible, and know we get to know it pretty well, and we can do some pretty cool stuff with it. There's been several talks using this platform, including at this Congress yesterday. So let's talk about GSM. This is what a GSM network looks like, and for the purpose of this talk, we will only focus on the air interface, that is all the communication between the phone and the network. The internal architecture of the network, we don't have to simulate the internal stuff and stuff like that. As long as for the phone we appear as a network, we're good. So if you look at the air interface, this communication over the air, it's of course decomposed into different layers. The IO layer is layer 3. It's itself decomposed into several sub-layers like resource management, mobility management, call management, and it's basically all the IO level logic of the phone. There is the specification reference in case you want to read them. Then just below that you get layer 2, which is the data link layer, which I find is a very boring layer because its primary purpose is just to handle packet retransmission and things like that. There's really nothing interesting about it. And then we get to layer 1, which is the physical layer, and we'll basically handle transmitting L2 packet over the air to the network or to the phones. Itself can be decomposed in two parts. The one I would call the channel coding. So basically, you take layer 2 packet, you add things like forward error correction, convolutional coding, CRC, things you need when you transmit data over the air and you want the data to be actually received clearly. And the second part is the actual RF part. That is, you take the bits and you somehow modulate them and transmit them to whoever you want to transmit them to. You're probably familiar with the fact that GSM uses different frequency bands depending on where you are in the world. It also uses, within each of these bands, 2 different subbands. This is a system that's called frequency division duplex. That is, all the information that is sent from the phone to the network is on one subband, and all the information which is sent from the network to the phone on a different subband. And you can probably already see why this might be a problem for us. Each of those frequency, each of those pair of frequency actually is attributed a specific number called the RFkin. So, if I say RFkin 512, well, it's going to be the downlink on 1505.2 megahertz and the uplink on 1710.2 megahertz. So that's instead of transmitting an absolute frequency, they just transfer a number. And finally, in the RF transmission, precision is very, very critical. We're talking 0.1 ppm, so that's part per million, and that's for a relaxed specification of specifically for Pico BTS. If you take the macro BTS, so the big cell sites, they have even tighter specification than this. So, what is exactly sent on those frequencies? Well, all the transmission happen in bursts. And there's 4 main types of burst. The first one is called normal burst because it represents pretty much 99% of the traffic. This is the kind of burst you use when you want to transfer actual payload data. The three other types of bursts have very specific functions, which are used, I would say, rarely compared to the normal burst. So the first two types are frequency correction burst and synchronization burst. Those are sent only by the network, and they are received by the phone, and they allow the phone to essentially synchronize to a cell, discover very early timing information and things like that the phone will need to actually, camp to the cell, discover its identity and things like that. The fourth type of burst is called access burst, and it's used by the phone when it wants to establish a dedicated channel. So usually, when your phone is not doing anything, it's not transmitting, it's basically just receiving broadcast information from the network. At some point, if your phone wants to do something actually useful, it needs to establish a dedicated communication channel with the network, and the first step of that process is using the access burst. And they are very, very special bursts that will be transferred on a shared uplink channel. So those bursts are not just transmitted at random times. GSM is a fully synchronous system that has been described by several people as a TDMA nightmare, because you essentially have TDMA inside TDMA. If you take the continuous stream of data on the RF frequency, you will find 8 time slots that compose a frame. So you got time, they transfer time slot 0, time slot 1, and so forth, and then they just repeat itself. And this is the first layer of time domain multiplex, where each time slot is actually completely independent to the other. They represent, each of them represent what's called a physical channel on GSM. And the things that would be useful for later is to know that the time slot on the uplink and downlink band don't happen at the same time. So the time slot 0 for the uplink band actually happens 3 time slots later. And it has been done that way because a phone will only be on one channel at a time, okay? And they wanted to avoid the requirement for a phone to have to transmit and receive at the same time. And so they just shifted them in time so that your phone, when it's communicating with the network, it receives a burst, switch from RX to TX, transmit a burst, then switch from TX to RX, and receive a burst, and so on and so forth. This makes the phones simpler and cheaper. So the second layer of TDMA, I would say, is what's called multiframes. So on each of these physical channels, depending on the frame number, you will have a specific burst that you will find there. So let's say that this is a multiframe, okay? And so you take the frame number, you do the frame number modulo 51 in this case because the multiframe has 51 bursts. And if it's equal to, let's say, 10, well, you're going to find a FCCH burst. And this multiplex essentially creates logical channels inside the physical channels. When you put everything together, you get something like that. It might look complex at first, but eventually you get used to it. You just have to remember that the time is really important in GSM, and everything is sent at a very specific time. So now that we know a little bit about GSM and how a network acts, we need to know exactly how a phone works, or more specifically, well, this phone, since it's our target today. So if you just look here, well, it all starts with the antenna. I mean, it's a standard antenna, nothing special about it. It's directly connected to the transmit and receive switch. As I said, the phone can transmit and receive at the same time, so they just use a switch. If we look at the receive path, the signal from the air is transmitted to a RX filter, so basically it will filter out any out of band interference and things like that. It's down converted using what's called a mixer. It's down converted to baseband. It's sampled by the chip called the analog baseband, and the information is sent to the actual digital baseband, which is itself composed of a DSP and an ARM core. If you look at the transmit path, so how the phone actually transmit bursts, it's pretty much the same thing, except in reverse. That is, you send data to the analog baseband, it's up-converted, then it's amplified because you need to transmit with some power to actually get to wherever the antenna is. and it's sent to the antenna. One thing to note, though, is this block. That's a hardware modulation unit. So in the receive pass, it pretty much acts like a software-defined radio. So all the demodulation stuff is implemented entirely in software in the DSP. While for the transmit pass, the modulation is actually done in hardware, which means the transmit pass is slightly less flexible than the receive pass. For our purposes, it doesn't really matter that much because well, all the bursts all use the same modulation, which means we can use that hardware modulator without too much issues. So this is pretty much what I described. There's some more precision about the digital baseband. So that's what we call the calypso chip, the calypso chip itself. So I said it's composed of a DSP and an ARM core. Unfortunately for us, the DSP uses a mask ROM for its firmware. Which of course is not that good for us, but more on that later. And the DSP pretty much implements all the low-layer, layer 1 functions. The ARM core, well, as I said, we already have Osmocom BB, which is an open-source baseband implementation. Osmocom BB works, and so the ARM core is pretty much under our control, which means we can do whatever we want with it. So, now that we know what a GSM network looks like and what the phone looks like inside, how do we make the phone act as a network? Well, it all starts with layer 2 and layer 3. So these are the upper layer, as I mentioned before. The main difference here is that the roles are swapped, obviously. But it's not much of an obstacle because even in cheap phones like that, all of this is implemented in software. So we can just strip it out, all the software, and replace it by our own software. Of course, that means that we need to implement it. Hopefully, well, open source stacks already exist. There's actually 2 of them. The OpenBSC plus Osmo BTS combination can implement the network side layer 2 and layer 3. And there is also a project called OpenBTS, which also has layer 2 and layer 3 inside it. So we can just reuse those. And what we'll do for now is we run those on the host, also on a standard laptop PC, and communicate with the phone using a serial link. So we can reuse them as is, which is good. Then we get down to layer 1. Well, as I mentioned, it's entirely in the phone. It's pretty much entirely implemented in DSP, and it really doesn't do what we need it to do because, first, it will only allow you to, you give it L2 packets and you receive L2 packets. It doesn't let you play with the burst and all the low layer stuff. And even if you wanted to reuse it, it anyway doesn't support multiple channels at once. So it's really no good to us. That means that we need another implementation of layer 1. So the first part of layer 1, as I mentioned, is channel coding, and we can find that in those projects. Not in OpenBSC and the Osmo BTS combination. Unfortunately, this actually relies on commercial hardware, which have their own closed-source implementation of the channel coding. But OpenBTS relies on generic SDR hardware, like it uses a USOP or more recently the UMTRX, which means it has its own channel coding implementation. And even better is that they have nicely split OpenBTS already into 2 applications. The OpenBTS binary itself, which implement the layer 1 channel coding, the L2, L3, and the external SIP interface. And then transceiver interface, which transmits and receives raw burst on the air. Which means it's perfect for us because we can just take the main OpenBTS application, completely unmodified, and just replace the transceiver binary with our own that will, instead of using a USOP, will use phones. Of course, it's easier said than done, because when you get to actually transmitting raw information on the air using the phone, things get interesting. As I mentioned before, uplink and downlink use separate bands. So the phone usually receives the downlink and transmit on the uplink, and the hardware is kind of tied to that. More specifically, the mixer part, up conversion and down conversion, are really only specified to work in their respective band. Now, two things that play in our advantage is the bands actually overlap. So, for example, GSM 850 downlink just happened to be pretty much within GSM 900 uplink. Same thing for DCS 800 and PCS 1900. It doesn't solve all the problems, but as we saw with sniffing with those phones, those chips, I mean, they don't just stop working when you get slightly out of spec. They continue working, and turns out they can be driven out of spec far enough that it doesn't pose much of a problem. The other thing is duplexing. So phones don't transmit and receive at the same time. On the other hand, a BTS absolutely has to transmit a continuous beacon so that when phones scan for network, they will find it. The phones, when they scan for the network, they essentially look first for RF power on the channel, on that frequency. And if they find RF power, then they will look a little deeper. Well, phones can transmit and receive at the same time. So we could have a phone that transmits continuously, but then it cannot receive anything, which means it can't do anything useful. There are two solutions for that. The first, I mean, yeah, you either have to use multiple phones to transmit and receive at the same time, because with one phone, I mean, software is not going to turn a switch into a duplexer. So you either use multiple phones, like one to transmit and one to receive, or you just attempt half duplex operation. The first option is probably the best and will be more reliable, but you need two phones and it's more complicated, so I choose the second, at least for now, which is half duplex operation. So what exactly does that mean? Well, that means that I don't transmit a continuous beacon, and I pretty much just hope that the phone will find me. Turns out it works better than I expected. It's not perfect, so I will probably change it at some point, but for now it will do. So what's called the time slot layout is essentially how I partition the time between transmit and receive. As you can see, all the T are transmits and the R are receive, so I pretty much only have, I said that, on one frequency you have 8 physical channels. Well, I pretty much only have one useful one. But it's enough to transmit a beacon and have control channels. It's unfortunately not enough to place a voice call yet, but I hope to solve that soon. So, and the problem is timing. As I said, GSM networks need to be very precise timing-wise. 0.1 ppm. Unfortunately, the crystal that you will find in phones are, cheap crystal. They're like 20 ppm of error. So there is like 2 orders of magnitude in difference in the required precision. Fortunately, the crystal in your phone is voltage controlled, which means you can actually lock the crystal of your phone to a commercial cell, and that's what I do here. So what happens is that instead of starting the BTS directly, I just start listening, find a commercial cell in the area, lock all the timing to it, that is the oscillator, the TDMA patterns, and that kind of thing, and then I start broadcasting the BTS when I'm locked, and I periodically adjust my timing to the commercial cell to make sure that that I stay in sync. This works actually much better than I expected. The only downside is, well, you need a commercial cell around. You can't just start that BTS in the middle of the desert when there's no coverage, because it won't have a reference cell. Actually, if you're in the middle of the desert, it might actually work, because if you don't have a reference cell, your cell phone doesn't have a reference cell either, so it might just lock to it anyway, but yeah. So these were still pretty easy to solve compared to what's ahead, and that's the DSP. The DSP is pretty much the only piece of hardware that has access to the radio interface, so you can't just bypass it, you have to use it. As I said, it's based off mask ROM, which means we can't just flash it with our own firmware. In any case, we certainly don't want to replace the entire firmware because it would be a lot of work to write one. But hopefully the DSP firmware developer, they make bugs. Not on purpose, of course, but and so the DSP has a mechanism to allow to fix those bugs even if it's a mask ROM. Basically, a lot of the functions are just called indirectly using jump tables, and those jump tables are in RAM, and the DSP gives you the opportunity to override those pointers with your own function pointer, and so instead of calling a function in ROM, it will call a function in RAM that you put there, and the DSP will actually execute your code. Dispatching is done using the bootloader. We discovered it. I mean, the bootloader is essentially very similar to what you find on the TI OMAP chip of the time, because they reuse a lot of the IPs, obviously. And so, what this bootloader does is you upload a function to the shared memory between the DSP and the ARM. You give the DSP a start address, and it will start executing code there. And so you can load the default jump tables, patch in your function, and then jump to the real start address of the DSP. Of course, if we want to patch the DSP, we actually have to analyze it first. And if we want to analyze it first, we actually need to dump it first. Since we have code execution, the DSP, this might appear easy, but it turns out that it has a security feature where any code that's executing from RAM can't read anything which is stored in ROM. So essentially, we just guessed that somewhere in the ROM there had to be a function called memcopy. We tried every possible address for it, and just waited until the DSP didn't crash. And this way we can just copy the ROM chunk by chunk into RAM, where we can read it from the ARM code. And then we had the image of the DSP ROM. The next step, of course, is to analyze it, because you essentially get it's not that big. It's like 256K, if I remember correctly, but it's binary code. It doesn't have a single string in it, and you don't. I mean, we had the start address, so it's good already. But to identify the various parts of the firmware and be able to track them down, the best method we found, at least in this application, is to use the interrupt, because when each time a GSM frame starts, an interrupt is triggered. Each time a burst is transmitted, an interrupt is started. Each time the DMA for reception is finished, sorry, you get an interrupt. So using those points, you can quickly find out how the burst transmission is done, how the modulation is done, at least where it's done. And the frame timer allows you to essentially control the interface between the ARM and the DSP. So what did we add as functionality to the DSP? The first thing was multi-slot transmit. So by default, as I said, the phone only transmits on a single time slot. If I just transmit on a single time slot, absolutely no phone will find the network, because I transmit like 1/8 of the time, to 12.5% of the time. I mean, chances are the phone will never see me. And in any case, I want to have more than one channel, hopefully. So we need to transmit several bursts at once. We know the hardware is capable of doing it, because that hardware is certified for GPRS, and GPRS actually has multi-slot. So it was just a matter of programming the DSP appropriately, which turned out to be easier than I thought. I thought multi-slot ticks would be something really hard to do, and to play with double buffers for the hardware modulators. And it turned out it pretty much just worked once we got a capture of how to do it. The same thing isn't true for multi-slot RX. I thought that multi-slot RX would be easy, that receiving several consecutive bursts, you could just do one big DMA or just let it run. Turns out it doesn't really work at all like that. You have to set a back-to-back DMA, and somehow they refuse to work. And that's something that's really annoying right now. And definitely the next item on my to-do list is to make multi-slot RX so that I can receive more than one time slot. If you remember the timing layout that I said here, I'm currently only have one R here because I can't set a second. If I set a second, it just does nothing. And so that's really something I need to work on. But I mean, even with a single physical channel, we still have enough to get recognized as a valid network. The third thing was, if you remember the start of the talk, I mentioned the 4 different types of bursts, and more specifically the FCCH and SCH bursts. Those are only transmitted by the network, which means the phone has absolutely no function to send those bursts. So those had to be implemented, the transmission of those bursts. Transmitting normal bursts, well, the phone usually does that, but it does it in a way that doesn't fit us, because we want to transmit arbitrary normal bursts. The phone usually transmits those bursts for a specific logical channel, and we want to support multiple logical channels. The final functionality that we had to add to the DSP was receiving of RACH bursts. So when the phone wants to establish a channel, it will send, as I said, a special burst called RACH. And if you want the phone or network phone, I would say, to recognize those bursts, we need to actually implement the demodulation of those, because usually they transmit those, but they don't receive them. The way it's been done currently is shortcut. That works well. So basically what we do is we look at the RF power on the channel, okay? And usually there is nothing, it's just the noise floor, which is hopefully not too high. But as soon as the phone will start transmitting those bursts, of course the RF power in the channel is going to rise. And when it rises, we actually just take the IQ data, we send it to the PC, and we do the demodulation there. Because it's much easier to code the demodulation routine on on your laptop than try to encode it in C540 assembly. Because of course, I mean, when you're essentially patching the code of the DSP, but you put your own code in RAM, but it's not like TI provided us with a map of what address was free and in RAM and what address wasn't. So we have very little space where we can actually put stuff without breaking other stuff. So we want to really be as small as possible, and that's why it has pretty much to be coded in assembly and by hand. So if you look at the spectrum of what it looks like, so for you that are not familiar with a waterfall diagram, which is actually in the other direction. In this direction you have time, and this is frequency, and this is just the FFT of the signal essentially. And you can see that it's discontinuous because of the half duplex operation. So here I'm transmitting something, then during this time slot, well, I need some time to retune the PLL. It's just not instantaneous. It doesn't take a full time slot, but once I've lost the start, I can't use it anyway. Then here in the middle, I receive a burst, which you can't see obviously, but then I retune again to prepare for the next transmission, and then transmit 5 bursts, and this goes on. And you can see these parts, which are zoomed here, they're the frequency correction bursts. They're essentially pure tones in the frequency domain. And I mean, if you were familiar with GSM, you would recognize that this is a BCCH multiframe. So I'm going to try to make it work. Keep in mind that this is a proof of concept. So, wait. How do I put this thing? Oh, right. So essentially what I'm going to do is first connect one of those phones to a serial cable. Any serial cable that works with Osmocom BB will work. There is no real speed requirement, at least for now. Yeah, probably. Well, actually, yeah. Unfortunately, I have no idea how to do that. I'm sorry, I really have no control over the video output of my laptop. It's beyond my technical skills. Anyway, you'll see that the text will go so fast that you can't read it anyway. But so what I'm doing here is using Osmocom. That is, I'm loading a new firmware on this phone. So this is the first step to do. No, demo. The second one is to set up OpenBTS. So you actually have to start SIP serve because else OpenBTS just doesn't do anything. Oh yes, so as I said, you need to use a commercial cell as reference for timing, which means I actually need to select the cell here. So I'm not actually using a commercial cell here, I'm just using the test GSM network that we're broadcasting from the balcony, because, well, that's pretty much the strongest network here, of course. So let's see, it's on RFGAN 871. So the step that you have to do is load the firmware, configure OpenBTS, install and configure OpenBTS, which I've already done. There are plenty of how to configure it. Select the cell that you're going to use as a reference, which I just did here, selecting the RFCAN of the cell that's broadcasted from in here. And then you need to select the frequency at which you want to broadcast. You should only broadcast, of course, on frequency you have valid license for. We have a license here, 869. It's currently in use, so I'm just trying to broadcast stronger than the network in here. See if hopefully that works. Then you just start OpenBTS. OpenBTS itself will start the transceiver application in a moment, and the phone is synchronizing to the commercial network, then OpenBTS starts to transmit burst, and this is hopefully broadcasting a BCCH now. If we look at Wireshark, oh, right. First one, 29. So we can see that it's broadcasting. Yes, okay, so apparently someone has already found the cell because I already have a location update request. So, and in theory, it's supposed to have delivered an SMS, which we should see here. SMS deliver, and broadcasting, welcome to GSM test network, UMZ. Is it someone here that received that SMS, or is it someone outside? No. So yes, it works. I mean, if you find, sometimes you will have trouble finding the network. Thank you. But if you insist a little, it will eventually work. We're trying to make it more reliable, as I said. Sometimes it can take time. I mean, since the phone just booted up, it will actually, its crystal is going to change temperature in the first, few minutes, and so sometimes you actually have to wait a few minutes. So yeah, you see there's actually plenty of activity. At some point, it's going to overload the phone. Because when I test it, I'm pretty much alone on the network. Here, there is pretty much every foreign SIM is going to try to register on the network and be refused, but it's still going to use the channel. So yeah, there's a lot of activity. So I'm sure some of you are wondering about the availability of that code. Well, it's going to be released very soon. The only thing missing is pretty much the documentation, because if I just put the code out there without any documentation of how to start it, it's just going to be a mess. I mean, even if we write documentation, there are still people that can't read it. As I said, a proof of concept. It's mainly targeted at developers or GSM enthusiasts. The slightly downside is that if you don't have an obvious error message and you just can't find the network or can't register to it, pretty much the only way of debugging that is with a spectrum analyzer, which of course might not be available to everyone. I would say that if you can run Osmocom BB, and that's pretty much a requirement, it should be fine. I mean, I've already sent the code to several people who managed to run it without too much trouble. Obviously, you should get a test license because it's bad to broadcast on frequency you don't have the right to. And just, in general, try to use your common sense. And some people might, rely on GSM working in their area for critical stuff. So in summary, well, I think I answered the question, is it possible to make a phone act as BTS? Yeah, kind of. It's not perfect, but it will do. In general, pretty much whatever device you take, it's much more fun to try to abuse it than just use it as it was designed. And yeah, reverse engineering is fun. I mean, you spend a lot of time staring at code and things like that, or trying to figure out why something doesn't work. But at the end of the day, when you finally make it work, it's really worth it. Well, at least for me. What's left to do? Well, a lot, of course. One thing that I know somebody is going to start working on this very soon is implement OpenBSC and Osmo BTS interoperability. Improve the reliability, as I said. Try multi-phone operation, see if that actually improves the reliability, because with multi-phone operation, I mean, currently I don't have any voice channels, which is a shame, but with multi-phone operation, I could potentially have a complete cell that has, up to 7 voice channels, which would be pretty great. I took a bunch of shortcuts, especially in things like timing advance and power control. They're really regulation loops in GSM that are used when your subscribers are far away. Here it doesn't matter that much. As I said, multi-slot RX, that should actually have been the first, because that's definitely what I'm going to be working on. Not only because it can help a lot this application, but this can also help a lot sniffing. So in general, I'd like to say thanks to everyone working on open source GSM and open telecom projects, because we need more people. In particular, here I'd like to thank Harald Weld and Dieter Spar for starting Osmocom BB, because obviously without that, this wouldn't exist. And David Burgess and all his team as Range Networks, well, for publishing and releasing OpenBTS as open source. And of course, the 29 C3 organizers for accepting my talk and having me here. If you want more information, you can refer to those websites. I mean, reading the GSM spec might sound like it's pretty boring, but I posted some reference on which one to read if you're interested, and there's a lot of information. And, I mean, you don't have to read the spec from page 1 to page 498. You can just skip a little. And that's it. Thank you for your attention.
That was some serious engineering. Okay, if you've got any questions, please line up at the microphones. We only have about 5 minutes, so hopefully we can get through a few.
What do you expect in terms of performance out of one or two phones and the software developed as far as you can imagine it now?
As performance, do you mean range? Or
range, number of clients to be served, all that.
Okay, so as I said, right now I only have one physical channel, and half of that is used for the actual beacon channel. So you can only have 4 control channels. To give you an idea, the cell we're running here for the network have 8 control channels. So it's only half. It's not that bad, but it won't serve any voice calls. For that, I really need multi-phone operation. When multi-phone operation is working, I would expect to have at least 6 voice channels on it, so pretty much a full GSM cell. As for range, power regulation isn't really implemented yet, so the power is hard-coded to some fairly low level, but it's obviously not that small since someone here got an SMS that's not in this room. So, does that answer your question?
Yeah, pretty much. That sounds like once you get your issues out of the way, it could be
yes,
it could be really record-breaking low range hardware doing extremely interesting things.
Yes, if the 2-phone operation work like I think they will work, it will be pretty much like a BTS. Okay. It's not entirely compliant with all the small details of the specification, like spurious emissions or modulation accuracy or things like that, but it's not that far.
We have time for 2 more quick questions. Right side.
I was wondering, is it a big deal to get a test license? Because I could imagine that, for example, the Bundesnetzagentur is not that willing or used to give away test licenses to private persons.
It will highly depend on your country. I have no idea of what institute you. I suppose it's a German. Yeah. Okay. I know it's possible to get test license in Germany, since we have got one here for like 10 BTS and up to 3 watts. And as to individuals, yes, that might be a problem. I know at least in Belgium, they will pretty much only hand them out to company. No matter how small the company, you kind of need just some stamp of a company on the request form. Yeah.
Thanks. Do we have any questions from IRC? Hello, Internet.
Okay.
Yes?
Yes. Do you need to rework the uplink filters on the Motorola phones to get this to work?
Okay. On this phone, they are not. It depends on your application. If you're doing desktop testing or room testing, it's actually better to leave them on, because they help filter out, they help prevent the input front end from saturating. If you were trying to shoot for maximum distance, then you would remove them. But this phone doesn't have the filter removed, and it worked fine. So, yeah.
Okay, great. We got time for 1 more. Anyone left?
Yeah.
Somebody?
So, as far as I understand, now you're running the software on PC mostly. So you're using the phone just as a receiver transmitter.
Yes, exactly.
How hard would it be to move the software to the actual phone so you don't depend on the PC?
The problem is, the phone was designed to have CPU power to support only 1 channel at a time. Here we have to have something like something like pretty much 4 or 5 logical channels at minimum to encode and decode. Well, at least to encode. which means I don't think the phone has the computing power to do that. If you want a portable solution, the best shot would be like the Open Mocha phone, where you have an ARM core running Linux next to the Calypso baseband, and so you can run part of it on the application processor and then let the Calypso baseband as is. There are several other phones that are like the Open Mocha, where you have really an application processor to do the GUI and stuff like that connected to a Calypso baseband. But just the Calypso baseband, I don't think it will work.
Thank you.
Oh, okay, that is all the time we have. Thank you for the detailed answers. If you have further questions, please come find Sylvan after the talk. Once again, please thank him. That was excellent.